audible? Hello? Can I start? Is that issue is resolved? Hello? Yes, Manjusha madam, Prajakta madam. Can I start?
Sorry for inconvenience. Sorry, sir. Sir, I request you to go to 2 to 3 slides back. Sorry once again.
From that slide, is it open? Applications? Yes, Manjusha madam. Am I audible?
Yes, sir.
So can I start?
Yes, sir. You start.
Thank you. So that example that I want to discuss with you all, that paracetamol, when we scan that paracetamol in usable spectrophotometer in different solvents, you can able to understand the concept of bathochromic and hypsochromic shift in point per normal NOH. That lambda max value is 257 nanometer, while in case of our water as a solvent, the lambda max is 249 nanometer, and if that solvent is point per normal HCl, the lambda max is 244 nanometer. So if that basic pH, we can observe the bathochromic shift, and in that acidic pH, the same drug it will show the hypsochromic shift. So the same type of shifts can be observed when that molecule is interacted with the excipients. If that interaction is there, that time ultimately there is a change in the lambda max value of the drug, and it will confirm that the drug is interacted with your excipients or the polymer those are used in the formulation. And if there is a no shift in the lambda max value, it can give you an idea about the drug is not interacted with your excipients. So many of that applications are there for our drug, uh, that excipients, that formulations. So you can able to check the solubility of drug by using visible spectrophotometer, by phase solubility study, as well as many of the compounds they have different or pH dependent solubility in acidic, in neutral pH, in basic pH. The compounds on the basis of their pK value can able to conclude or predict that what will be the solubility pattern for that drug. So some are pH dependent solubility patterns are there, so you can able to predict it, as well as you can able to determine that degree of ionization, the compatibility of drug and excipients also, the rate of reaction which is to be processed. So if the drug A is there and if that other drug B is there, A and B are interacted in that reaction chamber or vessel, and after 30 minutes, 1 hour, 2 hours, if you pull the sample from that reaction chamber or vessel, you can just identify the formation of new product. So here, suppose that lambda max of A is 230, lambda max of B is 250 nanometer, and the product which is to be formed, that is C, suppose, and the lambda max for C is 300 nanometer. So after 30 minutes, 1 hour, 2 hour, you can understand in that spectrums that there is a decrease in the intensity of A and B at 230 and 250 nanometer, and there is a increase in the or arrival or appearance of the peak at 300 nanometer that indicate there is a formation of that reaction product, that is C molecule. So after some time, that 2 hours or 3 hours, when that reaction is completed, so when you scan that sample in UV visible spectrophotometer, you can observe that there is a complete disappearance of peaks at 230 and 250 nanometer, and there is the arrival of new peak with a bigger intensity, that is hyperchromic shift at 300 nanometer. So there is a rate of reaction can be calculated by UV visible spectrophotometer, as well as the dissolution and diffusion studies during formulation development of many of that formulations. You can able to determine the rate of dissolution and amount of drug which is to be diffused or dissolved by UV visible spectrophotometer by just scan that aliquot quantity of sample from the dissolution or diffusion apparatus, as well as during stability study, photolytic degradation study, and oxidative degradation studies of the drug molecules. You can use that usable spectrophotometer for the check at what rate the drug is degraded and at what rate that stability is to be observed. And the determination of shelf life can be achieved by this usable spectrophotometer by RNA sequestration. So that methodology. So whenever the new chemical entity or new unknown molecule or drug is there in your hand, and that time that aim is or objectives are to determine the lambda max, to plot the calibration curve, how to select the solvents. So that selection criteria for the divisible spectrophotometer is depend on the solubility of drug in that solvents. So that solvents can be selected. Next is that plot of calibration curve in that same solvent in which the drug is having highest solubility. After that, and the condition is that these solvents those are selected, they are transparent to the UV and visible regions. Their lambda max values must be below 190 nanometer. After that, example is the benzene. The benzene lambda max is 280 nanometer. So benzene will not be selected as a UV solvent. So next, that calibration curve is plotted, and here that solvent in which the different concentration of drugs are prepared. So the concentration range is to be selected on the basis that the absorbance value will fall in the range of zero point 0.1 to zero point 0.9. And for diffusion and dissolution studies, so as our dosage form which is to be formulated, if it is administered via oral route and it goes into the stomach, that time our dissolution medium is initially you can select it as a point for normal HL if that monograph is not available. If we prepare the enteric coated tablets or granules or microspheres, that time that our dissolution medium is positive buffer solution of pH 6.8, as that upper part of intestine, that pH of that fluid is started from 5.5 to 5.6. You can use that pH 5.5, 5.6 or 6.8. If our formulation it is a orodispersible tablet, mouth dissolving tablet, maybe if you prepare the chewing gums, lozenges, chocolate as a formulations for utilizing that Brahmi, right? Some herbal formulations are there, and if that compounds are able to absorb the UV light, that time that dissolution medium is our simulated salivary fluid, and the pH value it match with the saliva. So this is a methodology. So here that UV spectra of the drug XYZ in ethanol and that possible buffer pH 5.5. So here I selected that solvent ethanol because drug is having highest solubility in ethanol. That's why. And that second solvent which I selected here, that is possible buffer pH 5.5. So that ethanol is selected in order to determine the drug content. And here the possible buffer, the plot is there. because you have to conduct the dissolution study or diffusion study for the drug. That's why the other that medium is to be selected. In many of the cases, some of that steroid molecules, the arrival of two or three peaks are there at different lambda max values, maybe at 250, 300, 400, and 30 nanometer. So question is for the researchers, which lambda max we have to select. So that lambda max with the highest intensity and the lambda max at which at lower concentration 2 or 1 to 5 microgram per ml. If that R square value is 0.999 and that absorbance values for that range are in between zero point 0.1 to zero point 0.9, that time you can select that particular lambda max value. Next, so plot of calibration curves in both the solvents. One is ethanol and other is the phosphate buffer solution pH 5.5. So by using this, when you subjected your formulation for dissolution or diffusion studies, that time at what rate the drug is dissolution it is to be followed, or at what rate the drug is diffused, it follows which kinetics mechanisms. So that is to be predicted. So once you are able to determine the drug concentration at particular time interval, how much amount of drug is released or diffused from the formulation, so from that values, you can plot the different graphs and you can able to find out. So our formulation follows which type of kinetics. So if it is a microspheres are there or granules or powder formations are there, that time it may follow that Higgson's and Krauss kinetics model. If that formulation it does not depend, that release does not depend on the polymer, so it will follow the zero order kinetics. For sustained release formulation, it is a first order kinetics. For diffusion models, it is a executive plot is there. So you can able to predict that kinetic models also. So next is the FTIR. So in that infrared Fourier transform spectroscopy, it is also one type of absorption spectroscopy in which you can confirm the drug molecules which is in the state of solid, liquid or gas by using the different that sample assemblies. So here during pre-formulation and post-formulation studies, the confirmation of drug in pre-formulation and after that post-formulation, the compatibility studies is our drug is interacted with of the excipients those are utilized, that is to be investigated by the FTIR. So in that pre-formulation, that is the initial stage of product development. So that data can be submitted as a part of dossier to the different regulatory agencies that our drug molecules are not interacted with the excipients those are utilized, and on the basis of that you can conclude that the drug is efficacious, safe, it is stable in that specified packaging material in which the formulation is to be packed. So here, so that IR spectroscopy, as it is a absorption spectroscopy, and in that mid infrared region, that is 4,000 to 400 centimeter inverse, that is wave number, in which that chemical bonds that organic compounds having ability to absorb that IR light, and they are going to vibrate, they are going to bend, they will show that rocking, stretching, bending, and that stretching vibrations, and many more that vibrations are there. So here, how that IR spectroscopy it is helpful in the development of formations, that we discuss it here. So here, as it is a transmission mode, so you can able to understand how that peaks are. It is a reverse peak. If you just compare with that UV, the plots are there. So at specific wave number, the light which is to be absorbed, that time the transmittance, the degree of transmittance is less. So it is that you can able to predict that specific wave number of light it is to be absorbed by your compound. So each peak indicates that functional group or that particular bond within that molecule or that compound. So maybe C single bond C, that is for alkane, that stretching vibrations are observed at 2950 to 3050 centimeter inverse. If it is C double bond C, if that molecule is alkene, that time for that C double bond C stretching vibrations, that peaks are observed at 3050 to 3150 centimeter inverse. And for that alkyl molecules at C triple bond C, So that time that stretching vibrations are there, which are observed at 31502 to 3250 centimeter inverse. So likewise for alcohols, for ketones, for aldehydes, carboxylic compounds, there is a specific fingerprint region is there for seeing single bond O stretching. So if that peaks here are observed at nearer to that wave number values, you can able to conclude that this may be a that ketone, aldehyde, carboxylic acid or alcohols. So and for that easy understanding, you have to plot that overlay spectrum of the drug molecule for that excipients and drug and excipient that formulation which is to be optimized. And from that overlay spectra, which is shown in the diagram here, it is easy to differentiate that what is that addition of new peak or deletion of the peaks are there in order to recognize or understand is there any interaction between drug and excipient or is there any that cross linking is observed in between that drugs and polymers those are utilized. So here, lot of applications are there for that IR spectroscopy in that formulation development. That is identification of the drug formulations, identification of the additives or polymers those are used in that dosage form, detection of drug excipient compatibilities, detection of drug polymorphism, that for stability of the formulations, confirmation of complex of drug with that polymer, characterization of that nanosystems, those are formulated, maybe that nanoparticles, liposomes, neosomes, in the characterization of microspheres, and for the formulation of physical mixtures, those are prepared during the enhancement of solubility by the solid dispersion method. So we'll discuss that one by one, so you can understand it in more detail. So just observe that spectra, which is the overlay spectra of ibuprofen tablet, and the excipients those are used. So just understand that spectra here at 1721.5 centimeter inverse, there is a sharp with highest intensity peak for that C double bond O stretching, which indicate that that present of that ibuprofen in the tablet. So just see that first one, this is for that ibuprofen pure drug, and these dotted lines, it indicate that formulation, that is tablet in which ibuprofen is added. So if that sharp or characteristic peak of ibuprofen for C double bond O, if that peak is observed in our formulation also, you can able to understand that formulation in which that ibuprofen is present. So this is for that formulation spectra. Likewise, for your own formulations, you can able to just take that overlay spectrums and you can able to find out what is my characteristic P for my drug molecule, and you can predict that the drug is present or not. So of the absence and presence of drug can be confirmed by FTIR. So here the various excipients in the dosage forms. So here that spectrum is for magnesium stearate, second is for microcrystalline cellulose, and third one is for the grevia. So after that, the next two peaks are there in which the grevia with the magnesium stearate and the grevia with the MCC. So here the band at 2900 centimeter inverse, this is for magnesium stearate, which is observed here. It confirms the presence of stearate, and that broad spectrum is there. This is a broad spectrum which indicate the presence of grevia at 3400 centimeter inverse. So if that broad spectrum is there, from that which is observed in our pure sample of grevia, that same peak is observed in the mixture of grevia and MCC. It confirms that the presence of grevia. Likewise, you can able to understand that interaction between the excipients also. Next, polymorphism, which is the most important characteristic that is required to be checked if that molecule exhibit the polymorphism. So in case of that paracetamols, that is orthorhombic and the monoclinic polymorphisms can be shown by that molecule. So here you can understand in between 350 to 550 centimeter inverse. Just see that there is a shift in that absorption spectrum. That okay, there is a shift in that wave number values, that spectrums here, that indicate that the presence of orthorhombic and the monoclinic polymorphism which is exhibited by the paracetamol. So if you added that orthorhombic paracetamol that particular form of drug molecule in that formations. And if that peak values at 460 centimeter inverse, if that peak will be shifted to 470 centimeter inverse, that indicate that is a paracetamol orthorhombic, it will be converted into the monoclinic form. And in that many of the cases, some polymorphic that forms of the compound are therapeutically inactive. So that's why it is important to check that molecule undergo that polymorphism or not. Next is that stability point of view. So here that arrival of that peaks. So here this that highlighted portion is there in which, so this is a negative peak and that positive peaks are observed. Okay. So here in that first and second peak where that ibuprofen is there, and second that blue is that for ibuprofen, and here the spectrum for that drug with that four excipients, which is denoted by the green line. So here, in case of ibuprofen, 1721.5 centimeter inverse, the peak must be observed. While in that formulation, there is a positive peak is observed. That indicate there is some sort of things are there that drug molecule is interacted with the excipients used. Next, this is my own PhD work in which the drug is not interacted with the excipients those are used. So here that A peak is for the rosiglitazone maleate, B is for the Utrazit S100, and C is the optimized formulation. So here that hollow macro cavities formulations are prepared. So we can able to understand the spectral pattern for the drug and Utrazit here 1728.22 centimeter inverse for that esterified carboxylic acid group. It still show their bands in that spectra. So we can able to understand if that same spectra are observed in that our optimized formulations also. You can understand that our polymer which is to be used is not interacted with the drug. Now here, so this is for the drug and that polymers are not interacted with the each other. So that time you have to just confirm that all the peaks are observed. Okay. So if that all the peaks are observed and there is a no shift of specific peaks at particular wave number from this value to the another value, or there is a complete disappearance of peak, it indicates that the drug may interacted with the polymer. So this is for it, means there is no interaction. And here, whenever we prepare some dosage form that is a graphene nano composite molecules, ceramic nano composite molecules, carbon nanocomposite molecules. That time, or suppose here that example that I displayed here, that is O-carboxymethyl chitosan and that carbopol, both are interacted with each other. So this is the inner core of carboxymethyl chitosan and this is inner core of carbopol. So that amino group of CMC and that carboxy COC minus group of that carbopol, those are interacted with each other and that hydrogen bonding takes place, which results in the cross-linking. So if there is a cross-linking is there, such a type of, if you prepare the new polymers, next generation polymers, or the drug is interacted with your polymer, or drug is interacted with excipients, and you will form a new complex. That time, how FTR is there, or FTR is a tool which is helpful to just predict that or confirm that interaction is observed. So just understand here. So this A peak is there for O-carboxymethyl chitosan. B peak is for that O-carboxymethyl carbopol beads, and C peak is for the pure carbopol. So just understand the peaks observed for that carbopol and for O-carboxymethyl chitosans. And this B peak is for the O-carboxymethyl chitosan carbopol beads. So there is a disappearance of these peaks. You can see disappearance of these peaks and that arrival of new peak is there at a different wave number. It confirms that the O-carboxymethyl chitosan and the carbopols are interacted with each other and cross-linking takes place. So by FTIR, you can confirm it. Okay. So this is for discussion related to that particular spectra. So here that in case of evaluation of nano formulations, if we prepare that nanoparticles, suppose that chitosan nanoparticles, So in case of that chitosan nanoparticles, you just observe that spectra here. This is for pure chitosan is there, and this is for chitosan nanoparticles. So here in that chitosan, that peaks are observed at 1657 centimeter inverse and 1598 centimeter inverse, while this peak shift to 1639 to 1557 centimeter inverse in the FTR spectra, which is more specifically for C double bond N, which is caused by the interaction between the amino group of chitosan and the phosphate group of tripolyphosphate molecule, which is used during formation of the chitosan nanoparticle. So that interactions can be confirmed by this shift of that spectrum from 1657 to 1639 and 1598 to the 1557. So it confirms there is interaction between the amino group of chitosan and the tripolyphosphate, in which that phosphate group is interacted with the amino group of the chitosan. So again in that next, whenever you prepare the liposomal formulations, so that time here suppose that polyethylene glycol 2000 is there, and that second spectrum is for polyethylene glycolated liposomal for the drug molecule vedolactone. So here in case of that liposomal formulations, that spectrum is observed at 1090 centimeter inverse, and initially it will be observed at 1110 centimeter inverse. So there is a slight shift in that spectrum from by 20 wave number 1110 to 1090. It can confirm that there is a formation of the liposomes. Next is here that neosome formulations for that vancomycin hydrochloride. So this is A is for that free drug molecule, B is for that unloaded neosomes, and C is for the loaded neosomes. So just observe the peaks are at in case of pure drug at 1658 and 1502 centimeter inverse, and that there is sharp peak is there at 1230 with that lowest intensity. So in that unloaded neosomes, all these peaks are not arrived nor observed. But when you load that drug in that neosomes, that time you can able to understand that peaks are there for that loaded drug molecule. So from that you can confirm that the drug is loaded into the prepared neosomes. So loading can be confirmed or revealed by this FTI spectroscopy here. Next for that solid microparticulate systems. So for pure drug esomeprazole and for that microsphere, those are prepared. So just see in that spectra that B is for that microsphere and A is for that pure drug. So here there is a this broad spectrum is there, and this broad spectrum can be observed. So it confirms that this all the gastric peaks are there. So from that you can conclude that drug is enclosed or encapsulated into the microspheres. This is for that free mixtures. Physical mixture is there. This is free meloxicam. This is meloxicam 41. So all that peaks from which you can able to conclude that this is a broad spectrum. That sharp peaks are there. That small drift is there in that particular peaks, from which you can able to conclude that the drug is interacted with that excipients or not. And that next instrument that I want to discuss, that is role of differential scanning calorimetry, that is DSC, in that formulation development or pharmaceuticals. So that is DSC here. So all of you know that is a what is that mechanism and principle of DSC. So it measures that energy which is transferred to or from a sample when it undergoes some sort of physical or chemical changes, if that temperature is applied or that heat is applied. So that molecule may be degraded, molecule get melted, right? So it will be decomposed, it get oxidized, whatever the things that is to be happen, you can predict from the DSC. So DSC is able to monitor the changes in that substance if heat effects are associated with the physical and chemical changes. So more specifically, it is used to check the phase transition temperature, that is TG, that is glass transition temperature, TA for melting point, that heat capacities can be analyzed. So wide variety of applications are there of DS in pharmaceutical field, that is to measure the reaction kinetics, just like our UV, glass transition temperature, specific heat capacity can be determined, the compatibility of the drug, stability of the samples, effect of aging, that impact of excipients on crystallization, and for during in vitro characterization of the drug substances when we prepare the formulations. So here I just inserted one generalized thermogram for that XYZ molecule here. So from that you can able to conclude here that DS thermogram is there, that is in milliwatts per milligram. So here this is a baseline for the DSC curve. This is baseline. So when the molecule is just you apply that heat, that particular energy is applied per minute. So that time initially here there is a small drift is there in that baseline. So if that small drift is observed in our baseline, and again that straight line is there, so that small drift is indicate that it is a glass transition temperature for that molecule, and it is a characteristic property of every molecule, that glass transition temperature. So if that glass transition temperatures are shifted from that particular values to the next value, it indicates that the drug is interacted with the polymers. Okay, so here in that example the glass transition temperature is 77.7 degree Celsius. So as well as many of the molecules when they melted, that time they absorb the heat or they evolve the heat. So they may undergo exothermic or endothermic reactions. So here for exothermic crystallization, the peaks are likewise. Okay, positive peaks are there, and for endothermic meltings, that negative peaks are observed when we plot that milliwatt per milligram versus the temperature. In some cases, that plots are inverse. So that is there is a exothermic as a negative peak and endothermic as a positive peak. That time we have to check what is on that y-axis. Okay, it may be a delta H value. So just here, so heat of flow versus the temperature. So when our compound is solid or rigid, that amorphous molecule. So if this is for the glass transition temperature. So small drift is at baseline. After that, sudden that straight line after the glass transition temperature, it indicates it is a rubbery amorphous molecule. After that, this is a endothermic events are there, and these endothermic events may be for when the molecule absorbs the heat. At time, it will show it may be for glass transition temperature. It may show that melting of the drug. It may show that evaporation of that solvents. Those are hydrated, or in that volatilization will be there. There's a enthalpic recovery is there, or it that molecule undergo some sort of decomposition when that temperature is applied. So that negative peaks indicate this type of physical changes, as well as some that exothermic events are also there. So if that peaks are positive, that time it may indicate that crystallization, that cure reactions, or molecular undergo oxidation or decomposition in some cases. So here, this is also that PhD work of me and my friend. So you can able to understand just that A peak is for O carboxymethyl chitosan, B is for carbopol, and that C peak is for the O carboxymethyl chitosan carbopol beads. So here for that A, just that O carboxymethyl carbopol cross-link beads are presented here, and here the double endothermic peaks are in between 50 to 100 degrees Celsius. So these are double endothermic peaks are there. Okay, with the loss of water, it corresponds to the hydrophilic nature of our O carboxymethyl chitosan as a cross-linking polymer and the carbopol. And here that endothermic peak is there, which is related to the evaporation of water when it is exposed to the reflect the molecular changes, that is to be brought in after the cross-linking in between the O carboxymethyl chitosan and the carbopol. So from the DSC also you can confirm the two molecules, that two polymers are cross-linked with each other or not. So this is for one of the best example. From that you can able to understand how the DSC is utilized to confirm the cross-linking in between the different two polymers or the drug and polymer. So next is there is a DSC curve of uh, a drug. So here, DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is a DSC curve of a drug. So here, DSC curve of a drug is that excipient, and C is for mixture of A and B. So just understand. So peaks are for A, B, and C. So there is the slight changes in that melting point. So there may be interactions are will be there. So as well as when we plot the heat of flow versus temperature in the DSC curves, and here the melting points are there. So at lower degree Celsius, it indicates the compound is in amorphous form. If the temperature of melting is at towards a higher degree value, it indicates that the molecule sample, the drug molecule is in a crystalline form. So from that, you can also able to understand the nature of the molecule. Is it in amorphous or crystalline form? So this is that slight drift is there in that baseline. It indicates the glass transition temperature. That is the endotherm, which is a characteristic peak of our drug molecule. This is indicate that crystallization, and this is for the melting endotherm. So likewise for that interaction in between the drug and excipients. So here that is glass transition temperature, slight drift is there. Okay, this is for cold crystallization. So why it is called as cold crystallization? Because the temperature is nearer to 25 or 26 degrees Celsius. So it is below the room temperature 25 degrees. You can call it as the cold crystallization. So at this temperature, the molecule undergo the crystallization process. So that's why there is a certain sharp peak is to be observed. As well as to determine that dehydration and the desolvation, the DSC can be used. So usually at lower temperatures, that large enthalpy because of the evaporation of release of the water which is to be hydrated form or the solvent which is present with the molecule, and it may result in the lower hydrates and unhydrated phase and the amorphous phase of the molecules. So this is if that such a type of this is a glass transition temperature, and after that glass transition, if that suddenly there's a decline in the peak, this indicate that there is a dehydration and vaporization of the molecule. Okay, and after that the molecule undergo crystallization, and after that it will be show that it's melting peak at more than 180 or 190 degree Celsius. Okay, so such a type of peaks are there observed, and from that you can able to conclude that is that my molecule is in pure form or is it in impure form. That is confirmation of drug molecule, and is my drug is compatible with all the polymers utilized in that particular dosage form during pre-formulation studies. After that stability study, in order to predict the shelf life of the formulation, and as well as we can able to understand if the generation 2 3, just like our dendrimers are fourth level generation polymers are there. So is that polymer linking, that monomer units are linked to each other, and that fourth or third generation polymers are formed or not. So that is to be predicted, or by that cross linking between that polymer A and B is there, and when they are cross linked with each other, that time they are able to encapsulate the drug molecule into the cavity. So that is to be predicted by the DSC curves are also. Okay. So here, that's it from my side. So any questions? Yes.
Thank you so much, sir. If anyone have any questions, then put in chat box in our YouTube channel. Now I requesting to Prajakta Subramanya ma'am, please give the vote of thanks.
Good morning, everyone. It has been such an honor to be a part of this wonderful session. On behalf of organization, I would like to extend my heartfelt gratitude to our esteemed guest, Professor Dr. Bhushan Rane sir from D.D. Vispute College of Pharmacy, Panvel. Sincere thanks to our guests who worked on their respective area and topic for very long time to develop novel ideas and findings. Sir delivered a very knowledgeful lecture on different criteria that should be taken into consideration by the means of pharmacokinetics and pharmacodynamics while studying UV visible as well as IR, FTIR, DSC spectroscopies. How these techniques are taken into formulation, pre-formulation in the form of spectrometric analysis. Sir took very informative session about applications of IR in pre-formulations, applications of DSC in pre-formulation in the form of stability aspects to get optimized formulations. I would like to thank Principal of our college, Dr. Nitin Mohire sir, and organizer Professor Manjusha Sanap, and all organizing committee for arranging FDP on applicative and informative sessions. Thanks to participants present on YouTube live stream for making the time to be with us today and helping us make the session very successful. Thanks all. Thank you so much, sir.
Thank you very much, madam. And I'm thankful to the organizing committee of that EFDP.
Thank you so
And
much, ma'am. Now proceed further. I requesting to Professor Bhageshri Kohli ma'am, please give keynotes for next session.
Okay, thank you, madam. Now I welcome our second speaker, Dr. Rajendra Marathe sir, who is the principal of Government College of Pharmacy, Ratnagiri. Sir had completed his M.Pharm from NDM VPS College of Pharmacy, Nashik, and secured first division in M.Pharm and completed PhD from Government College of Pharmacy, Aurangabad. He worked as lecturer in Pravara College of Pharmacy. Later, he get promoted with his strive towards the success and achievement and got professor and principal post. Sir having 38 years of experience. This is about their academic experience. Now, I would like to share many things about the sir's academic achievements. His area of interest is spectroscopy, combined problems of spectroscopy, and synthesis of novel lead molecules. Sir has published 35 national and 15 international research papers. Sir has also published 2 books and 2 chapters of book. Sir has presented 15 papers on national level and 1 in international level. Sir has filed 1 patent too. Sir has guided 45 PG students and awarded 3 times. On final note, I would like to say we are very grateful for his presence among us today. Thank you, sir. Now, Dr. Rajendra Marathe, sir, I request you to start your session. Hello, sir.
सॉरी म्यूट होतं ते अनम्यूट
Okay.
केलं होतं.
Okay.
I am very much thankful to the management, Principal Dr. Moire and coordinator regarding this. You are exploring spectroscopic. I will not explore. Huh? I will just go into the basics because early in the morning I have ring to the coordinator. What about the name participants? They told that most of teachers are there, sir, from chemistry and analysis. Yes? Somebody should respond me. Huh? I am audible?
Yes, sir.
मग कोणीतरी बोलत जा मी काय विचारल्यानंतर. म्हणजे मग मी थोडंफार मराठीत बोललं चालेल का तुम्हाला? हॅलो, मग थोडं बोलत जा ना. मी काही विचारलं का लगेच रिस्पॉन्ड करा म्हणजे मला पुढे जायला बरं होईल. आता हा जो तुमचा टॉपिक आहे स्ट्रक्चर इल्युसिडेशन, बरोबर? आता मला पहिले सांगा स्ट्रक्चर इल्युसिडेशन मध्ये व्हॉट इज मीन बाय स्ट्रक्चर इल्युसिडेशन? कुणी आपले केमिस्ट्रीचे प्राध्यापक सांगा, अनालिसिस सांगा, सुटेकचे सांगा. मी खूप ग्राउंड लेवल पासून सुरुवात करणार आहे बरं. एनीवन? structure elucidation. What is meant by structure elucidation? First question, what is meant by what is the difference between the chromatography and spectroscopy? Spectroscopy, chromatography is a separation technique, and
Hello,
chromatography.
sir. To determine structure by various spectroscopic methods like
Okay.
IR, UV, mass, NMR.
Okay. First of all, I will tell about the chromatography and spectroscopy. Chromatography is separation technique, and spectroscopy is identification technique. In before spectroscopy, already we are identifying our structure on primary basis. From 11th standard, we have seen suppose acid group, aldehyde group, very basic fundamental test. Suppose, for example, nitro group, yellow compound nitro group. Yes, if you are doing nitration, after successful nitration, you will get yellow compound. Okay, this is the first happy thing to us. Then second, we will see their confirmation test. Yes, after confirmatory test, we have to go for perfect identification of that structure and confirmation. For confirmation means in short structure elucidation. Your spectroscopy starts from UV. Yes? Yes or no?
Yes, sir.
बोला. आता ऐका शांतपणे. ह्या ज्या 5 स्पेक्ट्रोस्कोपी आहेत, मी या 5 टच करणार आहे आणि थोडा वेळ मिळेल तर 2D वर पण बोलणार आहे. एकदम फंडामेंटल ग्राउंड टू द अर्थ बोलेल. फार मोठ्या मोठ्या तुम्हाला स्लाइड दाखवणार नाही मी. मी काय जादूगर नाही. माझी अपेक्षा असं असतं की शिक्षकाला काय आलं पाहिजे साधारणतः, आणि शिक्षकांनी विद्यार्थ्याला काय दिलं पाहिजे, या फंडामेंटल गोष्टी असतात. मी खूप एमफार्मचे डिझर्टेशन चेक करतो, पीएचडीचे करतो. आता एकदम सिंपल एक्झाम्पल सांगतो आयआरचं. जेव्हा हा विद्यार्थी आपला एमफार्मचा किंवा पीएचडीचा आयआर स्पेक्ट्रा लावतो आणि त्याच्या कुठेतरी त्या आयआर स्पेक्ट्राच्या व्हॅल्यू तो सगळ्यात शेवटी लिहितो. जेव्हा तुम्ही एखादा आयआर स्पेक्ट्रा कोट करता, मी जस्ट एक्झाम्पल घेतलं, आयआरचं घेतलं, मास एनएमआर सेम HNC खूप लांब येते, तर साधारणतः त्या आयआर स्पेक्ट्रामध्ये तुमचं स्ट्रक्चर दिसलं पाहिजे. त्याच्यानंतर त्या स्ट्रक्चर नंतर तुम्ही एक टेबल केला पाहिजे छान, त्याच्यात कोणते फंक्शन ग्रुप आहे. आता बरेचसे विद्यार्थी म्हणजे इव्हन पीएचडीचे, बरं मी काही एमफार्मचे बोलत नाही, सुरुवात करता CH स्ट्रेचिंग आणि CH बेंडिंग पासून. आता तुम्ही मला सांगा आयआर कशा करताय? आयआर इज अ फंडामेंटल स्पेक्ट्रोस्कोपी फॉर डिटर्मिनेशन ऑफ फंक्शनल ग्रुप. येस ऑर नो?
येस, सर.
मग आता CH स्ट्रेचिंग सुरुवातीला जर तुम्ही लिहिलं, तुम्ही म्हणजे आपल्या विद्यार्थ्याने पीएचडीच्या किंवा एमफार्मच्या, तर आपल्याला काय वाटेल? याचा अर्थ याला आयआर विषयी काहीच माहित नाही. तुम्ही पृथ्वी तलावरचा मला एखादा कंपाऊंड सांगा की ज्याच्यात कार्बन आणि हायड्रोजन नाही, म्हणजे CH स्ट्रेचिंग आणि बेंडिंग हे 2 पीक प्रत्येक कंपाऊंड मध्ये असतील. येस ऑर नो? येस ऑर नो? मी पहिलेच तुम्हाला सांगितलं, तुम्ही येस ऑर नो बोलत जा.
Yes, sir.
मग CH स्ट्रेचिंग आणि बेंडिंगच्या त्या टेबलमध्ये आपण पहिलं लिहिणं तुम्हाला संयुक्तिक वाटतं का? नाही. आता समजा तुम्ही एक कोणताही कंपाऊंड घेतला आणि कीटोन आहे त्याच्यात, तर सगळ्यात पहिले फंक्शनल ग्रुप आपला कीटोन आला पाहिजे. मग तो काही असू द्या, अल्डिहाइड असू द्या, ऍसिड असू द्या, इस्टर असू द्या, अनहायड्रेट असू द्या. मग त्या कार्बोनेटची रेंज आपण दिली पाहिजे. रेंज दिल्यानंतर पुढच्या कॉलम मध्ये आपल्याला कुठं तो पीक मिळाला हा दाखवला पाहिजे. आणि सगळ्यात शेवटी नाईलाज असतो CH स्ट्रेचिंग आणि बेंडिंग आपण लिहायचंय, कारण तो पीक तर हे दोघं पीक तर प्रत्येक कंपाऊंड मध्ये असतील. बरोबर? येस ऑर नो?
येस, सर.
आता पुढचं ऐका. मी या 5 स्पेक्ट्रोस्कोपीचे तुम्हाला 1 लाईन ऍप्लिकेशन सांगेल, दुसरं ऍप्लिकेशन पण सांगेल. मी फक्त 3च गोष्टीवर बोलणार आहे, 3च ऍप्लिकेशन सांगेल या सगळ्या स्पेक्ट्रोस्कोपीच्या स्ट्रक्चरल इल्युसिडेशन मध्ये. आता UV कशा करता वापरता मेनली? फॉर व्हॉट पर्पज UV इज यूज?
टू आयडेंटिफाय प्युरिटी ऑफ कंपाऊंड.
ओके. अजून
Concentration determination.
अजून मला जे आन्सर अपेक्षित आहे ते अजून कोणी सांगितलेलं नाही.
UV.
What is mean by chromophore? What is mean by absorption? What is mean by hyperchromic effect, hypochromic effect, transition state? हे जे तुम्ही जे ऍप्लिकेशन सांगितले हे आपल्या बी फार्म लेवल पर्यंत ठीक आहे. पण युव्ही विजिबल स्पेक्ट्रोस्कोपी काळजीपूर्वक ऐका, वेळ पडली तर लिहून घ्या. UV visible spectroscopy is mainly used to determine lambda max of conjugated diene, trienes, alpha beta unsaturated ketones. बरोबर, म्हणजे त्या कंपाऊंड मध्ये कॉन्जुगेशन आहे का नाही. जर कॉन्जुगेशन, आता युव्हीची रेंज तुम्हाला सांगून टाकतो मी, 200 to 400 nm. समजा लॅम्बडा मॅक्स आहे, जर 200 च्या पुढे आला तर समजायचं आपण त्याच्यामध्ये क्रोमोफोर आहे. व्हॉट इज मीन बाय क्रोमोफोर? क्रोमोफोर मीन्स ग्रुप रिस्पॉन्सिबल फॉर ऍब्झॉर्प्शन ऑफ युव्ही लाईट. जर तिथं क्रोमोफोरच नसेल तर यू विल गेट लॅम्बडा मॅक्स ऑफ दॅट कंपाऊंड बिलो 200. आता बरेच मी थेसिस बघतो एमफार्मचे पीएचडीचे, तिथं मोघम लिहितात ते लॅम्बडा मॅक्स आम्ही एवढा एवढा काढला. का काढला? तुम्ही जे स्ट्रक्चर डिटरमाइन केलं त्याचं बघा ना, त्याच्यात काय काय. कॉन्ज्युगेशन असेल तर तुमचा लॅम्बडा मॅक्स 200च्या पुढे असेल, जर कॉन्ज्युगेशन नसेल तर लॅम्बडा मॅक्स 200च्या खाली असेल. पहिली लाईन तुमची आली पाहिजे स्ट्रक्चर इल्युसिडेशन मध्ये युव्हीची. मी एक खूप सिंपल मॉलिक्यूल घेतलाय ग्लुटामाइन, त्याच्यावरच बोलणार आहे मी. मुद्दाम सिंपल खूप मी ठिकाणी बोलतो या ग्लुटामाइनवर. आता ते जर स्ट्रक्चर तुम्ही बघितलं, तुमच्याकडे मी ते त्या सानप मॅडम त्यांना पाठवलेले की तुमच्या डोळ्या पुढे असेल ना सगळं मी जे बोलतोय आता, ते ग्लुटामाइनचं स्ट्रक्चर आहे. येस ऑर नो?
येस सर.
हा, मग सांगा त्याच्यात कॉन्ज्युगेशन आहे का, क्रोमोफोर आहे का?
Glutamine.
माझ्या प्रेझेंटेशनचं पहिलंच पेज आहे, इंट्रोडक्शन.
Glutamine.
There is no conjugation in carbon-carbon bond, but there are two oxygen, sir. Two carbonyl oxygen.
ओके, म्हणजे याचा अर्थ की याचा लॅम्बडा मॅक्स किती येईल तुमचा या कंपाऊंडचा?
Below 200.
बिलो 200. म्हणजे युव्हीचा प्रश्न मिटला. युव्ही कॅन नॉट हेल्प इन दिस केस फॉर स्ट्रक्चर इल्युसिडेशन ऑफ ग्लुटामाइन. ओके, ऍग्री?
Yes, sir.
ओके. आता मी पुढे जातो IR वर, सेकंड ऍप्लिकेशन. Infrared spectroscopy is mainly used to determine presence of functional groups present in the compound. मी सध्या फक्त पहिल्या ऍप्लिकेशन बोलवले या सगळ्या स्पेक्ट्रोस्कोपीच्या. Infrared spectroscopy is a fundamental or basic research tool for any chemist, physics, chemistry, cognosy, ecology, etc. etc. to determine functional group. आता तुम्ही if you will see carefully this structure, there is a carbonyl group C double bond O. तुम्हाला पहिले कार्बोनिलचा पीक दिसला पाहिजे तिथं. Then amino group is there. Yes, OH group is there. Anyone of you can tell me how you distinguish primary, secondary and tertiary amine by IR spectroscopy. मला आन्सर अपेक्षित नाही, दिलं तर उत्तम, नाही दिलं तर अतिउत्तम.
Sir, number of hydrogen atoms present with the nitrogen.
What about the range of amino group?
Amino group 3200 centimeter inverse, and in case of secondary amines you will get primary amines you will get 2 peaks, whereas in secondary you will get single peak, and in tertiary you will not observe this absorption at particular wavelength.
Okay, good. Range of amines is between 3200 to 3500. In primary amine, if you observe carefully, there are 2 protons. You will get doublet. What is mean by doublet? In IR, singlet, doublet, medium peak, sharp peak, weak peak, broad peak. Doublet means main peak splitted into two times. In primary amine, there are two protons, so you will get doublet. In secondary amine, there is only H and H. You will get singlet. In tertiary amine, there is no proton, so in this range, tertiary amine will not show you peak. In this case of glutamine, you will get NH2 doublet between this range 3000 to, you always talk in case of range only. Huh? In beginning only I have told you. While posting your IR, in IR, you mention your structure. Below that, write one table, serial number, functional group, range, actual, and observed. But to me, what you observed, you write in next column that. Then we will say our conclusion. In my this whatever structure I have determined, in that there is a NH2 group, primary amino group, there is a doublet in this range, so given compound may be confirmed. Same thing, C double bond O group is there. Also observe carefully acid. Last group is acid. In case of glutamine. Acid gives broad peak between the range 2500 to 3000. This is the primary indication of acid in IR.
Okay, sir.
Yes, in acid group there is also OH group. OH gives IR peak between 3300 to 3500. And lastly, quote your below CH stretch and CH bending. But you start from primary amine, C double bond O, acid broad peak, then OH. Also, you know ether. What is the general sector of ether? COC.
Yes,
COC. Yes. In this acid also there is a CO and H. Means not full ether is there. Here is a half ether. CO dash, not next carbon. So ether's range is 1000 to 1100. In this region, if ether is there, you will get sharp peak. If half ether particularly observed in case of acid, ester and anhydride, you will get that peak weak. Weak means its intensity is less.
Okay.
Yes?
Yes, sir.
What I told you, understood?
Yes, sir.
Yes, sir.
Then you observe that there is OH group.
OH group.
Yes?
Yes.
OH
Yes, sir.
group always give broad peak. Yes? This is the first application of IR. Then I will go to the mass. I will calculate their molecular weight, whatever compound I have synthesized. And then I should get molecular ion peak on XYZ. Suppose molecular weight of this compound is something 100. I should get molecular ion peak. Molecular ion peak is the last peak present in mass spectroscopy, which gives molecular ion peak is the last peak present in mass spectroscopy, which gives the idea about molecular weight of compound. Unless and until I will get this peak, molecular ion peak, I will not say that I have synthesized this correct compound. If all of you are from Marathi background, in short, I will say you. बाप दाखवणे तर श्राद्ध कर. Chemistry analysis students, please remember.
Okay, sir.
मॉलिक्यूलर आयन पीक जब तक आप बताते नहीं तब तक आप मैं नहीं, कोई दुनिया में भर में कोई नहीं बोल सकता कि आपका कंपाउंड सिंथेसाइज हो गया.
Okay, sir.
Where students and research scholars and most of people are doing mistake here in mass spectroscopy. They are simply sending samples to the concerned organization for MS, but not telling them exact molecular weight. You observed whatever mass spectra students are attaching to their dissertation of MPharm, PhD, etc., etc. If you will tell them molecular exact approximate molecular weight of your compound, then he will scan in that range only. ते तिथं जे स्कॅनर बसलेले असतात, इन्स्ट्रुमेंट हँडल करणारे लोक असतात, त्या बिचाऱ्याला काय माहित असतं तुमच्या कंपाऊंडचं मॉलिक्युलर वेट काय आहे. तुम्ही जर त्याला अप्रॉक्सिमेट मॉलिक्युलर वेट पाठवलं नाही तर तो 2000 पर्यंत स्कॅन करून तुम्हाला पाठवल. आणि तुमच्या कंपाऊंडचं मॉलिक्युलर वेट 200 असेल तर 2000 कुठं 200 कुठं. यू प्लीज टेल देम की मॉलिक्युलर वेट ऑफ माय कंपाऊंड इज बिलो 300. So he will scan only in that rate. You will get your perfect peaks.
Yes, sir.
Got it or not yet?
Yes, sir. Got it.
Yes, sir.
I am just talking about the first application. म्हणजे तुम्हाला लक्षात आलं पाहिजे आपल्या विद्यार्थ्याला सुद्धा की त्याला आपण सांगितलं पाहिजे. उगा त्याला 1000 रुपये फी द्यायची तो मास स्पेक्ट्रा आपल्याला पाठवतो. आपल्याला काही कळत नाही, त्या पोरालाही काही कळत नाही, तो देतो थापून याच्यात छापून.
Correct, sir.
मग आता त्याच्यानंतर आफ्टर दॅट you observe which groups are present in your compound. Simply see in this glutamic acid there is the acid group. Means you should get P count 45. Yes? Fragmentation. What is meant by fragmentation? Fragmentation means just breakdown of the compound. You break down that compound in various fragments. Observe whatever you got EMS spectra from your source, from where you are getting it. Yes? Then I will talk about base peak next. Then next I will go to the NMR. How many types of NMR are there? Hello. तुम्ही काही स्लाइड दाखवू नका, अजून मी ते बघतच नाही. ते पहिले तुम्हाला मला पहिलं ऍप्लिकेशन सांगायचंय.
Their magnetic resonance.
How many types of NMR there?
NMR can be proton NMR, C13 NMR, and those who are having magnetic movement. All those compound are magnetic. We can have NMR for that compound.
Okay. Nuclear magnetic resonance spectroscopy. There are two types of spectroscopy: HNMR, proton nuclear magnetic resonance, and CNMR, carbon nuclear magnetic resonance. HNMR. Now listen carefully. HNMR, first application, just like UV and IR, HNMR gives idea about presence of different types of protons present in the molecule. किती वेगवेगळ्या प्रकारचे प्रोटॉन्स आहेत त्या मॉलिक्युल मध्ये ते आपल्याला HNMR ने कळतं. आता तुमच्या डोळ्यापुढे ग्लुटामाइनचं स्ट्रक्चर आहे. किती प्रकारचे प्रोटॉन आहे सांगा बरं?
1, 2.
ठीक आहे, तुमच्या आता लक्षात नसेल काही काळजी करू नका. अमायनो ग्रुप आहे, त्याचे प्रोटॉन आहे. परत तो C डबल बॉन्डवाला CH2 अटॅच आहे, परत CH2 अटॅच आहे, NH2 CH ला अटॅच आहे. म्हणजे 1 2 3 4 आणि OH चा एक प्रोटॉन आहे, 5. म्हणजे 5 सिग्नल. इफ यू ऑब्झर्व 5 सिग्नल, then you will say that my structure is perfect. You should get 5 different types of signal.
Okay.
Yes or no?
Yes, sir.
If you have any doubt regarding my any statement, you can ask immediately.
Sir.
So your doubt is clear.
Yes.
5 different types of proton. Okay. Then I will go for different types of proton.
That amino group, both amino group, they are having different peak.
This amino group will be big because there next my just wait for 1 minute. My second NMR gives HNMR, I will say PMR. PMR gives idea about environment of signal. What is meant by environment of signal? Anyone of you can tell me? Environment of signal. Sanga.
Electromagnetic environment in which proton is present. So here this E and F both are NH2, but both are having adjacent carbon atom with different electromagnetic environment. That's why they will give two different signals.
This NH2 group, somebody asked me question, no? This NH2 group having different environment. Environment means chemical shift.
Okay.
Chemical shift, what is the range of chemical shift? HNMR 0 to 12 delta. First NH2 is attached to C double bond O, second NH2 is attached to CH. So there will be, which will be shielded, which will be shielded. Shielded protons appear on upfield, de-shielded protons appear on downfield. Shielded protons requires less energy, de-shielded protons require higher energy, higher magnetic field.
Okay, sir.
Got it?
Okay, sir.
You tell me, which NH2 will come first in the chemical shift delta?
E.
Somebody told me no about electronegative atom. C double bond O. ज्यान NH2 ला अटॅच आहे तो नंतर येईल त्याच्या अगोदर हा NH2 येईल जो साध्या CH2 ला अटॅच CH ला अटॅच होतो. गॉट इट?
Yes. Yes, sir.
Yes. Same. I will move to the CNMR. CNMR is a spectroscopy used to determine presence of different types of carbon. आता you tell me how many different types of carbons are present in this domain?
4.
1, 2, 3, 4. See carefully.
1, 2, 3, 4.
There are 5 carbons. There are 5 carbons. All carbons are different. So you will get 5 signals in NMR spectra. Then we can say our compound is synthesized. Otherwise, no.
Okay, sir.
Yes?
Yes, sir.
You tell me, you know, any one of you know what is the chemical shift range of H and CNMR?
Proton NMR 0 to 12 and CNMR 0 to 220.
Very good. 0 to 220. In this compound, we have C double bond O group. So that ketone's peak will be the come above 200. So
Okay, sir.
easily we can say my compound contains C double bond O. Got it?
Yes, sir.
Also see the last acid group. What is the range of acid in CNMR? 180 to 200. When I will get peak in this range, I will say my compound is having acid group. Primarily already you have confirmed acid group. Just like our 11th standard acid, if you add sodium bicarbonate, you will get effervescence. Forget it. In IR also you will get peak, that broad peak between 2500 to 3000. Yes. In mass molecular weight also you have confirmed. But where this acid group is exactly, that will be shown by the CNMR. Got it?
Yes, sir.
Yes.
Yes, sir.
After okay, this is my first application of this 5 spectroscopy. UV determination of conjugation, IR functional group, mass, molecular weight, HNMR, different types of protons, CNMR, different types of carbon. 2D, after all, I will discuss about 2D NMR techniques afterward, just for 1 or 2 minutes. Lastly, second application, I will say XYZ spectroscopy means UV, IR, mass, HC, whatever it means, is used to distinguish among various isomeric compound. Yes or no?
Yes, sir.
Yes or no? Yes. Okay. Can you justify? If yes, simply.
So according to position of that functional group in that structure.
You just write all of your having notebook or whatever pad provided by the organizers. You write one molecular formula C2H6O. Wrote
H6O. Yes, sir.
C2H6O. Huh? C2H6O.
Yes, sir. Written.
You ask my question. This compound exists in 2 isomers. Right, 2 isomers. One
This
is
is
having.
dimethyl ether, sir.
जस्ट वेट घाई नका करू ना तुम्ही थोडं ऐकत असेल अजून मी प्रश्नच विचारला त्याच्यात तुम्ही उत्तर कसं दिलं हा मला प्रश्न आला
Sorry, sir.
एक्झिस्टिंग टू आयसोम एक मिनिट, existing two isomers A and B. A and B. Yes.
Yes, sir.
One of them giving IR absorption peak at 1050 centimeter inverse. And second hint, its MIP is on 46 and one peak at 31 and 15. Which is it? You got question? My question? माझा प्रश्न कळाला का तुम्हाला?
Sir, please repeat it once.
A compound having molecular formula C2H6O existing two isomer A and B. A isomer is having their IR absorption peak at 1050. Their base peak is at 31 and giving one HNMR signal and one CMR signal. ओके, तुम्हाला क्वेश्चनच कळाला नाही मला असं वाटतं.
We get it.
I don't know how you will solve, but I will say you how to solve such type of questions. How you will solve? Any one of you know a degree of hydrogenation, hydrogen ion deficiency?
Yes, sir.
What is hydrogen ion deficiency?
We have to calculate it by considering number of carbons.
You know the formula of this hydrogen ion deficiency? If you don't know, you write simply U is equal to, you write U is equal to, U, capital U is equal to C plus 1, capital C plus 1 minus 1/2 X minus N, capital X minus capital N. You wrote?
Yes, sir.
U means degree of unsaturation or hydrogen ion deficiency. If U is equal to 1, means given compound contains one double bond or one ring. Yes. If U is equal to 2, means given compound contains two ring or two double bond or one ring, one double. I will give you simple example of benzene. What is molecular formula of benzene?
C6H6.
H6. You add this benzene. You add this values in this formula. What is the U of benzene?
4.
4. Very good. You justify your. Means 4 means in benzene ring there are 3 double bond and 1 ring. 3 plus 1, 4. Got it?
Yes, sir.
समजलं ना? हे बघा, इथं जर कधी सुटीचे स्टाफ मेंबर असतील तर थांबा, मी तुमच्याकडे येणार आहे. हाऊ दिस स्ट्रक्चरल टेक्निक्स कॅन बी हेल्पफुल टू यू.
Yes, sir. Please,
I
sir.
want to just, I am discussing only the first application and second I have started, third not yet started, fourth will be my application to the Sutix and Cognosy and Ecology students.
Okay, sir.
Ecology faculty, sorry. U is equal to 4. Yes. Same thing. C2H6O. What will be the U of that compound? I have not told you about what is meant by X and what is meant by N. C means in this formula, U means degree of unsaturation, C means number of tetravalent atom means carbon, capital X means number of monovalent atom means hydrogen or halogen, and capital N means number of trivalent atom, nitrogen and other.
Okay, sir.
While determining U, ignore number of divalent atom means oxygen, sulfur. Yes, in this molecular formula C2H6O, oxygen is there. You ignore that. What is the U of this molecular formula C2H6O? किती आला U?
0.
Oh, 0.
0. Very good. When oxygen containing compound U is 0 means given compound may be alcohol or ether. Got it?
Yes, sir.
Ah. Now you tell me, I have told you I arranged 1050. This is I range of what?
Half ether.
Ether.
इथर. ओके, म्हणजे आता मला कोणतरी अगोदर कोणीतरी आन्सर सांगितलं होतं सर डायमिथिल इथर. मी एकदम ग्राउंड लेवलचा प्रॉब्लेम घेतला डायमिथिल इथर. आता नेक्स्ट माय क्वेश्चन, गिव्ह मास स्पेक्ट्रोस्कोपी गिव्ह पीक ॲट 31. 31 मीन्स व्हॉट? If you will get peak at 31 means OCH3 group.
Okay.
Got it? Oxygen 16, 16 plus methyl 15. 16 plus 15, 31.
Yes, sir.
Got it? Then I told you, gives one signal of HNMR. There are only one type of protons. Both methyl are equivalent protons. So they will give one signal. What is meant by equivalent proton and what is meant by non-equivalent proton? Equivalent proton means protons appearing on same environment. म्हणजे जिनकी chemical shift same रहती है उसको बोलते हैं equivalent proton. जिनकी chemical shift अलग रहती है उसको बोलते हैं non-equivalent proton. For example, see our glutamine structure. I have not yet opened second slide also. I am just sticking to the structure of glutamine. There are two CH2 groups after CONH2. They are equivalent or non-equivalent?
Non-equivalent.
Good. Why non-equivalent? Because first CH2 is attached to C double bond O, second CH2 is attached to CH.
Yes, sir.
These are the non-equivalent. While in case of dimethyl ether, both methyls are equivalent because their relatives are same. First methyl attached to C double bond O, third methyl attached, second methyl attached to C double bond O. In this case, this CH2 is attached to C double bond O, second CH2 is attached to CH. Yes? Also, their splitting is also different. First CH2 will give triplet, second CH2, what it will give? Second CH2, what will be the splitting? Kiti? Somebody told I will correct that. What she told I don't know exactly. Quadrant, no? Quadrant is correct, no? Because splitting n plus 1, number of protons on adjacent carbon plus 1. This CH2 attached to 2. First 2 proton and then CH. 2 plus 1, 3. 3 plus 1, 4. 4 means quadrant. Yes?
Yes, sir.
Come to the point. Then this compound structure is confirmed. This is the structure of dimethyl ether. Got it? In CMR gives
Yes,
two
sir.
signals because there are only two carbons. Both are equivalents. So only one CMR signal. Yes?
Yes, sir.
हे बघा मी जे बोलतोय तुम्ही सगळे शिक्षक आहे या हेतूने बोलतोय बरं. आता मला सांगा तुमच्यापैकी कोणाला रूल ऑफ 13 माहिती आहे का? एनी वन ऑफ यू नो रूल ऑफ 13? आता मी व्हॉट अबाउट आय टोल्ड यू राईट ऍटलीस्ट केमिस्ट्री अनालिसिस टीचर this formula carefully. Also, you know rule of 13. Any one of you know? Yes or no?
No, sir.
Huh?
No, sir.
No. Right.
No, sir.
Rule of 13. 13 means 1 3.
Yes.
Rule of 13. Write this formula carefully. Rule of 13 is used to determine probable molecular formula of the compound. Rule of 13 is mainly used to determine probable molecular formula of the compound.
Okay, sir.
Right formula. M by 13, capital M by 13 is equal to,
Okay.
capital M by 13 is equal to capital C. त्याच्या बॉटमला लिहा N. डॉट करा, डॉट करो. Then write capital H, hydrogen. Below that hydrogen write small n plus R. Small n plus R. Yes?
Yes, sir.
You wrote? I will repeat. M by 13, capital M by 13 is equal to C, capital C.
By N.
त्याच्या बॉटमला N dot H, capital H, N plus R means small n plus R. Now M means molecular weight of the compound. Capital M means molecular weight of the compound.
Okay.
Then capital C means carbon, number of carbon atoms. How many number of carbon atoms you see? Below that I told you write small n. Small n means numerator, bhagakar.
Okay.
Okay?
Yes, sir.
Then I told you H, capital H means number of protons. Below that I told you write N plus R. Small n means numerator, bhagakar. Plus R means remainder. Remainder means baki.
Baki.
Now listen carefully. This is the formula for rule of 13. Why the name given rule of 13? Any one of you can tell me?
Rule of 13.
Why the name given rule of 13? First line, I told you this rule of 13 is used to determine probable molecular formula of the compound.
Yes, sir.
Okay, why the name given rule of 13? Don't worry, I will tell you everything. I will tell you. Rule of 13 means 13 mass. What is the mass of carbon?
12.
12. What is the mass of hydrogen?
1.
1. 12 plus 1?
13.
My first line was rule of 13 is used to determine probable molecular formula of the compound. Means हाइड्रोकार्बन. कार्बन आणि हाइड्रोजन कितने हैं वो कंपाउंड में, उसके लिए रूल ऑफ 13 है. गॉट इट?
Yes, sir.
घाबरू नका तुम्ही. ऐका, मी एक छान एक्झाम्पल घेतो. बेन्झिन. बेन्झिनचं मॉलिक्युलर वेट किती आहे?
Molecular weight.
78, sir.
78. Now you put this value in our formula. M means molecular weight of compound. Means 78 divided by 13 is equal to C. कार्बन. N किती? भागाकार कितना? न्यूमरेटर कितना आया?
6.
6. In benzene there are 6 carbon.
Yes.
You now you tell me about H. H, below that I wrote N plus R. N means bhagakar.
Numerator.
6 numerator. And remainder baki.
0.
Baki 0. Means H is
6.
means what is the molecular formula of benzene?
3686.
Got it?
Yes, sir.
तुम्हाला भूक नाही लागली ना?
नाही सर.
आता ऐका, मजेशीर आहे. तुमच्यापैकी कोणाच्या मनात शंका आली नाही का? सर समजा ऑक्सिजन असेल तर काय करणार, नायट्रोजन असेल तर काय करणार?
यायला पाहिजे होती.
Shankar. If suppose given compound contains oxygen or nitrogen, what is the mass of oxygen?
16.
16. 16 means how many carbon atoms and how many hydrogens?
So CH3, 1 carbon, 3 hydrogen.
No, 4
Four.
hydrogen.
Four hydrogens. Correct. Means now whatever simple example I have taken of this dimethyl ether, this molecular formula is C2H6O. Huh? Come to the point. C